So in the last video, we looked at what happens when you move a conductor through a magnetic field and how it induces an electric current. That's only one way that you can do it, and there's actually a more common way of inducing a current that we're going to look at in this video, and that is by changing the magnetic flux through a circuit. So what is magnetic flux? The magnetic flux, which you will see this capital phi, the Greek letter phi, to represent flux. It's like a capital O and an I on top of each other. So the magnetic flux through some area A is a product of that area and the magnetic field, but only the magnetic field that is perpendicular to it. So if we try to write that in equation form, then phi is equal to B. Well, I need to get a symbol real quick here. Oh no, you're going to find out my secret. I get my Greek letters from Google. Alright, so it's B dot A. So we learned last unit how we can simplify a cross product since we're just doing algebra-based stuff here. So to simplify a dot product instead of sign, we'll just use a cosine. So we'll have B times A times cosine. I'll just write theta. So the magnetic flux is how much of a magnetic field is actually going through a certain area. And these pictures down below help us understand that a little better. So the area vector is perpendicular to the area. So that means if we have this loop here, its area vector would point straight out. So it would be pointing up along with the magnetic field. So it's the magnitude of the area vector is just equal to however big the area is. So if we try to imagine flux graphically, it's kind of like the number and length of flux lines that you have passing through a certain area. So we start out with a small magnetic field and a small flux, so little tiny arrows going through that circular area. In this next picture, we have a small area, which would also give us a small flux, but I mean, you can see that just from the equation. If you have a small b, you have a small flux. If you have a small a, small flux. And this is kind of the y, if we want to look at it visually. So if you have a small area, you won't kind of catch as many of the arrows. You can kind of think of it like a big net. How much of the magnetic field are you going to catch in that net? If you have a small cosine theta, you can see from the equation, you'll have a small flux. So if your area or your loop, your net, is oriented in a way that it's not going to catch any of the magnetic field arrows, you'll have a really small flux. So to get the largest phi, we want the largest flux, we want the area vector to be parallel to the magnetic field vectors. We want a big area, so a big loop, big net, and we want a lot of magnetic field lines running through, a lot of big magnetic field lines. So unit of flux, the unit that we'll use here is the Weber, which you will just see simplified as WB. So 1 Weber is equal to 1, our unit for magnetic field is Tesla, and our unit for area is meter squared. So 1 Weber is the same thing as 1 Tesla times meter squared. Alright, so we'll see in a second when we develop some equations later on that a change in magnetic flux, so delta phi, is actually more important than just knowing what phi is. So our interest is going to be in how flux changes, not in some certain value at some certain point in time. So the formula that we have for magnetic flux suggests that there's three ways that we can change it. So first way would be changing the magnetic field strength. So if we slide a permanent magnet back and forth, then the magnetic field through some certain area is going to fluctuate. Um, and apparently we're going to look at that a little bit later. Next way that we can change magnetic flux is by changing the area. So we're not talking here about just like flux A would be smaller than flux B because flux B has a bigger area. We're talking about for one system here, we want to be able to change the amount of flux we have. So we're going to be continuously changing the area. In the example above, we were continuously changing the magnetic field. So in the example we had in the last video with a bar sliding on rails in a magnetic field, we were actually changing the area. It was a square shape or a rectangular shape, and when we slid the bar across, we were expanding the size of our rectangle. So as it grows, the number of field lines that were going through that rectangle were increasing, and the flux increased as we moved the bar off to the right. And then last way we would be able to change the amount of flux would be to change the angle. So we'll say rotate the area that the flux is going through, and just in parentheses we'll call that changing the angle between A and B. So changing the angle between the area A and the magnetic field B. So if the area is perpendicular to the magnetic field, the flux is just the product of B times A, or A times B as it's written here, was BA in our equation. So whenever you rotate the area so that it's at some angle, you'll get fewer of the lines passing through, so your flux is actually decreasing. So you kind of, in this rotation, if you start perpendicular, or you start with the area vector parallel to the magnetic field vectors, then you have some total amount of flux. As you rotate it, it decreases, and then it would start to increase again, start to decrease again. So as you rotate, you kind of increase and decrease. So be careful with that. Alright, so example here. We have a square with sides of length 2 meters. It's perpendicular to a magnetic field of strength 10 teslas. If the square is rotated by, that should just be 60 degrees, we want to know what is the change in magnetic flux through the. So now we want to calculate, I still have my dot. Alright, so we want to calculate a change in magnetic flux, so a delta phi. So that actually looks a little bit different than the one I had before. I think I grabbed a lowercase one by mistake. Alright, so delta phi. So anytime you see delta, just remember that that means final minus initial. So we have to figure out what is the flux at the beginning and what is the flux at the end to be able to go any further with this problem and figure out what it wants. So Remember, our general equation for magnetic flux is B times A times cosine theta. So what's changing here? Is B changing? No, B stays the same through both. Is the area changing? No, we have a pretty fixed square. The sides are always 2 meters. So the thing that's changing here is theta. So I'm going to call this BA cosine theta F minus BA cosine theta theta I. Alright, so from here we can actually do a little bit of factoring because we know both of these things are the same. So it would be B times A times cosine theta F. Oh, what? Minus, oh my gosh, minus cosine theta I. So let's start plugging in the things that we know to figure out what is this change in flux. So we have magnetic field, the strength is 10 teslas. Area for a square is length times width. If one side of a square is 2 meters, then all sides are 2 meters. So we'd have 2 meters times 2 meters. And we'll multiply that by cosine theta F is 60 degrees. So cosine 60 minus cosine, the angle between A and B in the initial case is actually 0. The area vector and the magnetic field vector are perpendicular to each other. Don't let this bit confuse you. The square, yes, is perpendicular to the magnetic field, but the area of that square is parallel to the magnetic field. They run together. Alright, so we go through, run through, do that math. 10, 40. What do we have here? 1/2 minus 1. So 40 times negative 1/2, we get negative 20 Webers there for the flux. So our change in flux is a negative answer. The change in flux can be a negative answer. Did I write it down here, or do you have to write it in? You have to write it in. Alright, so magnetic flux decreases because as the square is rotated, fewer magnetic field lines are able to pass through it.